At first glance, the Earth beneath our feet appears stable, unchanging, reliable, permanent. Cities rise on it, civilizations depend on it, and history is written across its surface. But this perception is an illusion. Beneath even the most ordinary landscape lies a world that is anything but still. A few meters below the soil, temperature shifts, pressure increases, light disappears completely. Continue deeper, and the environment transforms into something entirely foreign: dense rock formations, flowing molten material, vast caverns, and hidden reservoirs stretching across unimaginable distances. The surface of Earth is not a foundation. It is a thin boundary separating two vastly different realities. Modern science has revealed that the crust, the layer we live on, is astonishingly thin compared to the rest of the planet. In some regions, it extends just a few kilometers before giving way to deeper, hotter, and more dynamic layers. Beneath continents and oceans alike, a hidden architecture exists, one that has shaped mountains, triggered earthquakes, and buried entire ecosystems over millions of years. Yet despite centuries of exploration, we have barely scratched the surface. The deepest hole ever drilled by humans reaches just over 12 kilometers. Beyond that point, extreme heat and pressure make further descent nearly impossible with current technology. Compared to Earth's total radius of over 6,300 kilometers, this is insignificant, a shallow incision into a vast unknown. So what lies beneath that limit? What structures exist in regions we cannot directly observe? And how much of Earth's true nature remains concealed beneath layers of rock, time, and pressure? To understand this, we must move beyond the surface and into the hidden systems that define the planet itself. A history buried in layers. Every layer beneath the Earth's surface is a record. Over billions of years, geological processes have created a stratified archive of the planet's past. Sediments settle, compress, and harden into rock. Volcanic eruptions deposit new material. Tectonic movements shift entire sections of crust, folding and fracturing them into complex formations. Each layer tells a story, but not in a way that is easily read. Unlike written history, geological records are fragmented. Sections are missing. Others are distorted or buried beyond reach. Entire periods of time are represented only by traces, fossils, mineral deposits, or chemical signatures preserved under specific conditions. In some regions, ancient riverbeds lie hidden beneath deserts, their paths detectable only through satellite imaging. In others, evidence of prehistoric oceans exists far inland, locked within limestone formations. One of the most striking discoveries in recent decades has been the identification of vast underground water systems, ancient aquifers that have remained sealed for tens of thousands of years. These reservoirs contain water that predates modern civilization, offering insights into past climates and environmental conditions. But these discoveries also raise questions. If entire ecosystems and landscapes can be buried and preserved, how many others have been lost entirely? How much of Earth's history exists beyond our reach, not destroyed but hidden? The architecture of the deep. To understand the hidden world beneath Earth, it is necessary to examine its structure, not as a static object but as a dynamic system. The outermost layer, the crust, varies in thickness depending on location. Beneath continents, it can extend up to 70 kilometers. Under oceans, it is often less than 10 kilometers thick. This uneven distribution reflects the processes that formed it: collisions, separations, and continuous reshaping through tectonic activity. Below the crust lies the mantle, a vast region of semi-solid rock that behaves more like a slow-moving fluid over long periods of time. Heat from the planet's core drives convection currents within the mantle, causing it to rise and fall in massive cycles. These movements are responsible for the shifting of tectonic plates, the large sections of crust that form continents and ocean basins. Where these plates collide, mountains rise. Where they separate, new crust is formed. Where they slide past each other, stress builds until it is released in earthquakes. Deeper still lies the core, divided into a liquid outer layer and a solid inner center. Temperatures here exceed those found on the surface of the sun, yet immense pressure prevents the inner core from melting. This layered structure is not merely theoretical. It has been inferred through decades of seismic research, where waves generated by earthquakes travel through the Earth and change speed depending on the material they encounter. But while this model provides a framework, it does not reveal everything. Within each layer are variations, unexpected structures, anomalies, and regions that do not conform to standard models. These are the true mysteries of the deep. Hidden caverns and subterranean worlds. Not all of Earth's hidden spaces are deep. Some exist just below the surface, vast cave systems that stretch for hundreds of kilometers, forming complex networks of tunnels, chambers, and underground rivers. These environments are isolated, stable, and often completely dark. Over time, they have developed unique ecosystems adapted to conditions that differ entirely from the surface. Organisms in these environments often lack pigmentation and eyesight, relying instead on other senses to navigate and survive. Some species exist nowhere else on Earth, having evolved in complete isolation. In certain caves, entire rivers flow unseen, carving new pathways through rock over thousands of years. In others, massive chambers form, large enough to contain skyscrapers. Yet many of these systems remain only partially explored. Mapping them is difficult, dangerous, and time-consuming. Narrow passages, unstable structures, and the absence of light create conditions that limit human access. As a result, large sections remain unknown. These are not distant or unreachable environments. They exist beneath forests, mountains, and cities, hidden in plain sight. Life in the extreme. Perhaps the most surprising discoveries beneath Earth's surface are not geological, but biological. For decades, it was assumed that life required sunlight. This belief was based on the role of photosynthesis, where plants convert light into energy, forming the base of most ecosystems. But this assumption was incomplete. In deep underground environments, scientists have discovered microbial life that survives without any access to sunlight. These organisms rely on chemical reactions, extracting energy from minerals and gases in their surroundings. Some exist at depths of several kilometers, under conditions of high pressure and limited resources. Others thrive in environments with temperatures approaching the limits of what is considered habitable. These discoveries have profound implications. They suggest that life is more adaptable than previously thought. They expand the definition of habitable environments, and they raise the possibility that similar forms of life could exist beyond Earth, in places once considered inhospitable. But they also highlight how little we know about the ecosystems beneath our own planet. If life can exist in such extreme conditions, what other forms might remain undiscovered? The limits of exploration. Despite advances in technology, exploring the depths of Earth remains one of the most challenging scientific endeavors. Drilling projects face extreme temperatures that can damage equipment. Pressure increases rapidly with depth, complicating structural stability. Even transporting tools and materials to deep underground locations requires significant resources. Remote sensing techniques provide indirect information, but they lack the precision of direct observation. As a result, much of what we know is based on interpretation rather than direct evidence. This creates gaps in understanding, areas where data is incomplete or uncertain. These gaps are not failures, they are frontiers. And like all frontiers, They represent both opportunity and limitation. When the ground moves, the hidden systems beneath Earth are not passive. They are active, constantly shifting, and capable of sudden change. Earthquakes, volcanic eruptions, and land subsidence are all surface expressions of deeper processes. They reveal the presence of forces that operate beyond our immediate perception. In some cases, these events occur with little warning. Stress builds along fault lines over years or centuries, only to be released in seconds. Understanding these processes is critical, but difficult. The structures involved are complex, and direct observation is limited. Predicting when and where an event will occur remains one of the most significant challenges in geoscience. What lies beneath is not just unknown, it is unpredictable. The illusion of completion. There is a common belief that Earth has been fully explored, that the age of discovery has passed. This belief is misleading. While much of the surface has been mapped, the subsurface remains largely uncharted. New discoveries continue to emerge, not because they were hidden intentionally, but because they were difficult to access or detect. Each discovery challenges assumptions. Each unanswered question reveals the limits of current knowledge. The idea that we understand Earth completely is not supported by evidence. In reality, we are still in the early stages of understanding the planet we inhabit. The depth of the unknown. Beneath every step we take lies a world that is largely unseen. It is a world shaped by forces that operate over timescales far beyond human experience. A world that contains records of the past, systems that influence the present, and uncertainties that will shape the future. We have built cities, developed technologies, and expanded knowledge, but all of it rests on a foundation that we do not fully understand. The deeper we look, the more complex that foundation becomes. And with each layer we uncover, the question grows more difficult to answer. Not whether Earth hides mysteries, but how many remain. Closing reflection. Human progress has always been driven by exploration, the desire to understand what lies beyond the known. But in the case of Earth, the greatest unknown is not distant. It is beneath us. Silent, vast, and largely unexplored. And until we understand it, we cannot fully understand the world we call home. From above, the ocean appears calm, an endless expanse of blue stretching beyond the horizon. Ships move across it, satellites map it, humans have crossed it for centuries. But this image is deceptive. What we see is only the surface. Beneath that thin boundary lies a world so vast, so extreme, and so unfamiliar that it rivals the mystery of outer space. In fact, more of the ocean floor remains unexplored than the surface of the Moon or Mars. The average depth of the ocean is nearly 4 kilometers. In its deepest regions, such as the Mariana Trench, it plunges to depths exceeding 11 kilometers, far beyond the reach of sunlight, beyond the limits of conventional exploration. Pressure at these depths is immense, over 1,000 times greater than at the surface. Temperatures drop close to freezing. Darkness is absolute. And yet, despite these conditions, life exists. The ocean is not empty. It is not silent. It is not fully known. So the question is not whether the ocean hides mysteries. The question is how much of it we have truly seen. A history of surface exploration. Human interaction with the ocean has always been limited by technology. For thousands of years, exploration meant navigating across the surface, mapping coastlines, discovering islands, and charting trade routes. The depths remained inaccessible, a vast unknown beneath wooden ships and early navigation tools. Even as technology advanced, progress into the deep ocean remained slow. The invention of sonar in the 20th century allowed scientists to begin mapping the seafloor indirectly. By sending sound waves downward and measuring their return, researchers could estimate depth and identify large structures. But sonar provided only a rough outline. It revealed mountains, trenches, and ridges, but not the details, not the ecosystems, not the complexity. To truly explore the ocean, humans had to descend into it. Early submersibles made this possible, but only briefly and with significant risk. Even today, only a handful of missions have reached the deepest parts of the ocean. The vast majority of it remains unseen. The structure of the deep ocean. The ocean is not a uniform environment. It is divided into distinct layers, each with its own characteristics. The uppermost layer, known as the sunlight zone, extends to about 200 meters. Here, light penetrates the water, allowing photosynthesis to occur. This is where most marine life exists: fish, coral reefs, and plant life. Below this lies the twilight zone, where light fades rapidly. Vision becomes limited. Organisms begin to adapt to darkness. Deeper still is the midnight zone, an environment of complete darkness. No sunlight reaches this depth. Temperatures drop, pressure increases. Beyond this are the abyssal and hadal zones, the deepest parts of the ocean, including trenches that cut into the Earth's crust. These regions are extreme, and yet they are not lifeless. Life without light. One of the most significant discoveries in ocean science came from the deep sea. In the late 20th century, scientists discovered hydrothermal vents, cracks in the ocean floor where heated, mineral-rich water escapes from beneath the Earth's crust. Around these vents, entire ecosystems exist. Unlike surface ecosystems, these do not rely on sunlight. Instead, they are based on chemosynthesis, a process where organisms convert chemicals into energy. Bacteria form the base of this system. Larger organisms, tube worms, crustaceans, and fish, depend on them. These ecosystems thrive in conditions once thought impossible for life. Temperatures fluctuate dramatically, toxic chemicals are present, pressure is extreme. And yet life adapts. This discovery changed our understanding of biology. It proved that life does not require sunlight. It expanded the definition of habitable environments. And it suggested that similar ecosystems could exist elsewhere, in the oceans beneath icy moons, far beyond Earth. The unmapped seafloor. Despite decades of research, the majority of the ocean floor remains unmapped in high resolution. We know the general shape of the seafloor, but not its details. Large areas remain blank. Underwater mountain ranges stretch for thousands of kilometers. Trenches descend into depths that are rarely explored. Vast plains extend across the ocean floor, largely untouched. The ocean is not just a body of water. It is a dynamic system that influences the entire planet. Currents move vast amounts of heat around the globe, regulating climate. Changes in these currents can alter weather patterns, affecting agriculture, ecosystems, and human populations. Beneath the surface, tectonic activity shapes the seafloor. Underwater volcanoes erupt, creating new land. Plates shift, forming ridges and trenches. Earthquakes occur beneath the ocean, sometimes triggering tsunamis that travel across entire oceans. These processes are not isolated. They are connected to global systems, and many of them are not fully understood. The risks of exploration. As interest in the ocean grows, so does the potential for exploitation. Deep-sea mining has emerged as a possible source of valuable minerals, cobalt, nickel, and rare earth elements essential for modern technology. But the consequences are uncertain. Deep-sea ecosystems are fragile. Many species have slow growth rates and limited ability to recover from disturbance. Mining operations could damage these ecosystems before they are even fully studied. There are also risks associated with drilling, pollution, and climate change. Rising ocean temperatures and acidification are already affecting marine life. Coral reefs are declining. Oxygen levels in some regions are decreasing. The ocean is changing, and much of that change is happening in areas we do not fully understand. Separating fact from fiction. The mystery of the ocean has given rise to countless myths and speculation. Stories of unknown creatures, hidden civilizations, and unexplained phenomena have circulated for centuries. While some of these ideas are rooted in curiosity, they often lack scientific evidence. That does not mean the ocean is fully understood. It means that the real mysteries are grounded in observable phenomena, complex ecosystems, geological processes, and environmental changes that are still being studied. The challenge is to distinguish between imagination and reality, to focus on what can be measured, tested, and understood, because the truth is often more complex than fiction. The expanding edge of knowledge. Technology is slowly changing our ability to explore the ocean. Advanced submersibles can reach greater depths. Improved sensors provide more detailed data. Satellite systems enhance mapping capabilities. Artificial intelligence is being used to analyze patterns in ocean data, identifying trends that were previously unnoticed. These tools are expanding our understanding, but they also reveal how much remains unknown. Each new discovery leads to new questions. Each mapped region highlights areas that have yet to be explored. The boundary of knowledge continues to move, but it does not disappear. The depths that remain. The ocean covers more than 70% of Earth's surface. It regulates climate, supports ecosystems, influences weather, provides resources, and yet it remains largely unexplored. This is not due to a lack of interest, but due to the sheer scale and difficulty of the task. The deeper we go, the more challenging exploration becomes. The more we discover, the more we realize how little we know. Closing reflection. For centuries, humanity has looked outward, toward the stars, toward distant planets, toward the possibility of life beyond Earth. But one of the greatest mysteries lies much closer, beneath the surface of our own planet. Silent, dark, vast. An environment that shapes the world above it in ways we are only beginning to understand. The ocean is not just a part of Earth. It is a hidden dimension of it. And until it is fully explored, which may take generations, the question will remain unanswered. Not whether the ocean holds secrets, but how many still lie beneath its depths. Backhand index pointing right next step. Type Episode 3. Main op key le agla. Episode by isi level ka cinematic plus viral documentary script lik dunga. Episode 3. Clapperboard Episode 3. Antarctica's Buried Secrets. A continent that refuses to reveal itself. At the southernmost edge of Earth lies a continent unlike any other, vast, isolated, and almost entirely concealed beneath ice. Antarctica is not simply cold, it is extreme. Temperatures can fall below -80 degrees Celsius. Winds reach speeds that can strip exposed skin within minutes. For most of human history, it was completely inaccessible, too distant, too hostile, too unforgiving. Even today, it remains one of the least understood places on the planet. But the true mystery of Antarctica is not what lies on its surface. It is what lies beneath it. Nearly 98% of the continent is covered by a massive ice sheet, averaging over 2 kilometers in thickness. In some regions, that ice extends much deeper, compressing, preserving, and concealing whatever exists below. Mountains, lakes, valleys, entire landscapes frozen in time. Antarctica is not just a continent. It is a sealed archive. And only recently have we begun to understand what it contains. The world before ice. Antarctica was not always frozen. Millions of years ago, it was a vastly different environment, covered in forests, home to rivers, and inhabited by diverse forms of life. Fossil evidence reveals the existence of ancient plants and animals that could not survive in today's conditions. This transformation did not happen suddenly. It was the result of gradual climatic shifts, tectonic movements, and changes in atmospheric composition. As Antarctica drifted toward the South Pole, it became increasingly isolated. Ocean currents began to circulate around it, trapping cold water and preventing warmer currents from reaching its shores. Over time, ice began to form. Layer by layer, snowfall accumulated, compressed, and turned into ice sheets that grew thicker with each passing century. What once existed on the surface was slowly buried. Not destroyed, but preserved. Today, beneath kilometers of ice, remnants of that ancient world remain. But accessing them is not simple. The hidden landscape. For decades, Antarctica was thought to be relatively uniform beneath its ice, flat, featureless, and unremarkable. That assumption was wrong. Using radar and satellite imaging, scientists have discovered a complex landscape hidden beneath the ice sheet. Mountain ranges stretch across the continent, some comparable in size to major ranges found elsewhere in the world. Deep valleys cut through the terrain. Subglacial lakes, bodies of liquid water trapped beneath the ice, exist in complete darkness, isolated for millions of years. One of the most significant discoveries has been the identification of vast networks of these lakes, connected by hidden channels. These are not small pockets of water. They are dynamic systems, influenced by pressure, temperature, and the movement of the ice above. In some cases, water flows between lakes, creating a hidden hydrological system beneath the continent. This changes how we understand Antarctica. It is not a static block of ice. It is an active environment, constantly shifting, interacting, and evolving. Life in isolation. Perhaps the most surprising aspect of Antarctica's hidden world is the possibility of life. Subglacial lakes, sealed beneath kilometers of ice, have been isolated for hundreds of thousands, possibly millions of years. They exist without sunlight, under extreme pressure, and in near-freezing conditions. Yet, evidence suggests that microbial life may exist within them. Samples extracted from some of these lakes have revealed microorganisms capable of surviving in these extreme environments. These organisms rely on chemical processes rather than sunlight, similar to life found in deep ocean vents. If confirmed, this has significant implications. It demonstrates that life can exist in complete isolation, under conditions previously thought uninhabitable. It also provides a model for studying potential life beyond Earth, on icy moons such as Europa or Enceladus, where similar subsurface oceans may exist. But studying these environments is difficult. Drilling through kilometers of ice without contaminating these isolated ecosystems requires precision, caution, and advanced technology. Every attempt carries risk, and every discovery raises new questions. The ice that records time. The Antarctic ice sheet is more than a barrier, it is a record. As snow falls and accumulates, it traps tiny air bubbles. Over time, these layers compress, preserving samples of Earth's atmosphere from different periods in history. By drilling ice cores and analyzing these trapped gases, scientists can reconstruct past climates, atmospheric conditions, and even major environmental events. These records extend back hundreds of thousands of years. They reveal cycles of warming and cooling, fluctuations in greenhouse gases, and evidence of natural and human-induced changes. This data is critical. It provides context for current climate trends and helps predict future changes. But it also highlights a vulnerability. As global temperatures rise, parts of the ice sheet are melting. And with that melting, the record itself is at risk. The fragile balance. Antarctica plays a crucial role in regulating Earth's climate. Its ice reflects sunlight, helping to maintain global temperature balance. Its cold waters influence ocean currents, affecting weather patterns across the planet. But this balance is not fixed. Rising temperatures are causing sections of the ice sheet to thin and collapse. Glaciers are retreating. Ice shelves, floating extensions of the ice sheet, are breaking apart. These changes have consequences. Melting ice contributes to rising sea levels, which can affect coastal regions worldwide. Changes in ocean circulation can alter climate systems, impacting agriculture, ecosystems, and human populations. What happens in Antarctica does not stay in Antarctica. It affects the entire planet. Myths beneath the ice. Antarctica's isolation and mystery have led to widespread speculation. Claims of hidden structures, lost civilizations, and unexplained phenomena have circulated for years. Satellite images are often misinterpreted. Natural formations are presented as artificial. But these claims lack credible evidence. Scientific exploration of Antarctica is highly regulated. Research is conducted by international teams, and findings are subject to rigorous verification. The real discoveries, subglacial lakes, hidden mountain ranges, ancient climate records, are documented, studied, and shared within the scientific community. This does not make Antarctica less mysterious. It makes it more complex. The true mystery lies not in unsupported theories, but in the vast, measurable unknowns that remain. The challenge of access. Exploring Antarctica is one of the most difficult tasks in science. Extreme conditions limit the duration and scope of missions. Equipment must be specially designed to withstand cold, wind, and isolation. Transporting materials and personnel is costly and logistically complex. Even with modern technology, large areas remain inaccessible. Remote sensing provides valuable data, but it cannot replace direct observation. As a result, much of Antarctica's hidden world remains unexplored. Not because it is impossible to reach, but because it is difficult to study safely and effectively. A continent still being discovered. Despite these challenges, exploration continues. New technologies are improving our ability to map and analyze the ice sheet. Autonomous vehicles are being developed to explore subglacial environments. Satellite systems provide more detailed data than ever before. Each advancement reveals new information. New structures, new systems, new questions. Antarctica is not a solved puzzle. It is an ongoing investigation. The weight of what lies beneath. Beneath Antarctica's ice lies more than rock and water. There are records of Earth's past, systems that influence its present, and uncertainties that will shape its future. The continent holds information that could improve our understanding of climate, biology, and planetary science. But accessing that information requires time, resources, and careful planning. Because once disturbed, some of these environments cannot be restored. Closing reflection. Antarctica stands as one of the last true frontiers on Earth. Not because it is untouched, but because it is not fully understood. Beneath its ice lies a hidden world, silent, preserved, and largely inaccessible. A world that challenges our assumptions about knowledge, exploration, and control. We have mapped the seas, we have explored the oceans. But here at the edge of the planet, beneath layers of ice and time, the unknown still remains. And until it is fully revealed, Antarctica will continue to hold one of Earth's greatest secrets. Backhand index pointing right next step. Type Episode 4. Main Agla episode, Lost Civilizations and Missing History, Isi cinematic level par lik dunga. Episode 4. Clapperboard Episode 4. Lost Civilizations and Missing History. The gaps in human memory. History is often presented as a continuous story, a clear timeline of events, civilizations rising and falling, progress moving forward in a predictable line. But this narrative is incomplete. Between recorded events lie gaps, periods where evidence is scarce, fragmented, or entirely missing. Entire cultures have vanished with little trace. Cities that once thrived are now buried beneath soil, water, or jungle, their existence forgotten for centuries. What we know about human history is based on what has survived. And survival is not guaranteed. Time erodes, disasters destroy, environments change. Records are lost, overwritten, or never created in the first place. This means that history, as we understand it, is not a full account. It is a reconstruction. And within that reconstruction are uncertainties, missing chapters that raise a fundamental question. How much of human history has been lost? Civilizations that disappeared. Throughout history, entire civilizations have risen to prominence and then vanished. Some declines are well documented, caused by war, environmental change, or economic collapse. Others remain unexplained. Archaeological evidence reveals the existence of advanced societies that developed complex systems, agriculture, architecture, governance, long before modern technology. Yet in many cases, these societies left behind limited records. Structures decay, organic materials decompose, written language, if it existed, may not survive or may remain undeciphered. In some regions, dense vegetation has concealed entire cities. In others, shifting sands have buried settlements completely. The discovery of lost urban centers in previously unexplored areas suggests that many more may exist. Not destroyed but hidden. The problem of preservation. The survival of historical evidence depends on conditions. Dry climates can preserve materials for thousands of years. Ice can lock environments in a frozen state. Sediment can protect structures from erosion. But in many parts of the world, conditions are less favorable. Humidity accelerates decay. Flooding erodes foundations. Vegetation overtakes structures, breaking them down over time. This creates an uneven historical record. Some regions appear rich in history because evidence has been preserved. Others seem empty, not because civilizations did not exist, but because their traces have been lost. This imbalance affects how history is interpreted. It shapes assumptions about where and when human development occurred. But those assumptions may not reflect the full reality. Hidden beneath the surface. Many of the most significant archaeological discoveries have been made not by chance, but through advances in technology. Satellite imaging, ground-penetrating radar, and aerial scanning have revealed structures hidden beneath the surface. Walls, roads, foundations, and entire city layouts. In dense forests, these tools can detect patterns that are invisible from the ground. In deserts, they can identify buried formations beneath layers of sand. These discoveries are changing our understanding of ancient societies. They suggest that human populations were larger, more organized, and more widespread than previously believed. They also indicate that many sites remain undiscovered. Beneath modern cities, farmland, and natural landscapes, there may be layers of history waiting to be uncovered. The role of catastrophe. Not all civilizations disappear gradually. Some are affected by sudden events, natural disasters that alter landscapes in a matter of hours or days. Volcanic eruptions can bury cities under ash. Earthquakes can collapse structures and shift terrain. Floods can submerge entire regions. These events can preserve as well as destroy. In some cases, rapid burial protects structures and artifacts from long-term decay. In others, it erases them completely. Understanding these events is essential for interpreting archaeological evidence. They provide context for why certain sites are preserved while others are not. They also highlight the vulnerability of human societies to environmental forces. The question of continuity. One of the challenges in studying ancient civilizations is determining continuity, how one society transitions into another. In some cases, there is clear evidence of cultural progression. In others, there are abrupt changes, gaps where one system ends and another begins with little connection between them. These discontinuities raise questions. Were these transitions gradual but poorly documented? Or did they involve disruptions that erased previous systems? In regions with limited written records, these questions are difficult to answer. Archaeology provides clues, but interpretation is complex. Different theories may explain the same evidence in different ways. This uncertainty is part of the investigative process, separating evidence from speculation. The idea of lost civilizations has often been associated with speculation, advanced societies that disappeared without trace, leaving behind mysterious structures or unexplained technologies. While such ideas attract attention, they must be evaluated carefully. Scientific research relies on verifiable evidence, artifacts, structures, environmental data, and reproducible findings. Extraordinary claims require substantial proof. In many cases, simpler explanations, natural processes, known cultural practices, or misinterpretations account for observed phenomena. This does not eliminate the possibility of unknown histories. It ensures that conclusions are based on evidence rather than assumption. The real challenge is not proving that something extraordinary existed. It is understanding what actually did. The expanding historical record. As research continues, the historical record is expanding. New sites are discovered. Existing sites are reanalyzed with improved techniques. Data is shared across disciplines, providing a more comprehensive view of the past. This process is gradual. It involves excavation, analysis, interpretation, and revision. Each discovery contributes to a larger picture, but also introduces new questions. History is not static. It evolves as new information becomes available. The influence of modern perspective. Our understanding of the past is influenced by present knowledge. Interpretations are shaped by current theories, cultural perspectives, and available data. As these factors change, so does the interpretation of historical evidence. What was once considered unlikely may become accepted. What was assumed to be certain may be reconsidered. This does not mean that history is unreliable. It means that it is continually refined. The goal is not to create a fixed narrative, but to approach a more accurate understanding over time. The depth of what is missing. For every discovered site, there may be others that remain hidden. For every preserved artifact, there are countless others that have been lost. This imbalance is unavoidable. But it also means that our current understanding represents only a portion of what once existed. The scale of human history is vast, and much of it has not been fully documented. Closing reflection. Civilizations rise, develop, and leave their mark. But not all marks endure. Time, environment, and circumstance determine what is preserved and what is lost. What remains is a fragmented record, one that requires careful interpretation and continuous investigation. The past is not entirely gone. It is partially hidden. And as long as there are gaps in the record, there will be questions. Not only about what we know, but about what we have yet to discover. Backhand index pointing right next step. Type Episode 5. Main Agla Episode Underground Ecosystems and Alien Life. Isi Cinematic Documentary Style Main Likdunga. Episode 5. Clapperboard Episode 5. Underground Ecosystems and Alien Life. Life where it should not exist. For centuries, life on Earth was thought to depend on sunlight. Plants capture sunlight and convert it into energy. Animals depend on plants. Entire ecosystems are built on this foundation. Without sunlight, it was believed, life could not sustain itself. But deep beneath the Earth's surface, far removed from sunlight, an entirely different reality exists. In complete darkness, under immense pressure, and often in extreme temperatures, life persists. Not just survives, thrives. These underground ecosystems challenge one of the most fundamental assumptions in biology. They exist in places once thought to be completely uninhabitable. Kilometers beneath the surface, inside rock formations, within deep cave systems, and even in isolated water reservoirs, microorganisms have been discovered, organisms that rely not on sunlight, but on chemical reactions for energy. This is not theoretical. It is observable, measurable, and real. And it raises a profound question. If life can exist here, where else might it exist? The deep biosphere. Beneath Earth's surface lies what scientists call the deep biosphere. It is a vast, hidden ecosystem that extends several kilometers into the crust. Unlike surface ecosystems, it is not easily visible. It cannot be seen from space or from the surface. It must be detected indirectly or accessed through deep drilling. Within this environment, microorganisms live in pores within rock, in underground water systems, and in mineral-rich environments. These organisms are adapted to extreme conditions. They do not rely on sunlight. Instead, they use chemical processes to extract energy from their surroundings. Some break down minerals. Others use gases such as hydrogen or methane. Their metabolic rates are extremely slow. In some cases, a single organism may divide only once every several thousand years. This challenges our understanding of what life requires. Life is not limited to the surface. It extends into the depths. Energy without the sun. At the core of these ecosystems is a process known as chemosynthesis. In this process, organisms derive energy from chemical reactions rather than sunlight. This allows them to survive in environments where no light penetrates. Chemosynthesis is not unique to Earth. It has also been observed in extreme environments such as hydrothermal vents in the ocean, where chemical-rich fluids escape from beneath the Earth's crust. But underground ecosystems are different. They are isolated. They are often cut off from surface ecosystems for thousands or even millions of years. This isolation leads to unique evolutionary pathways. Species adapt to their specific environments in ways that are not seen elsewhere. This creates biodiversity that is still being discovered, and much of it remains unexplored. Extremophiles, life at the edge. The organisms that inhabit these extreme environments are known as extremophiles. They can survive conditions that would be lethal to most known life forms. Some can withstand high radiation levels. Others thrive in high temperatures or extreme cold. Some survive in highly acidic or alkaline environments. These organisms are not anomalies. They are evidence of life's adaptability. They demonstrate that life is not fragile, it is resilient. And that resilience expands the boundaries of where life can exist. If life can survive deep beneath the Earth, it can potentially exist in other extreme environments. This has significant implications for the search for life beyond Earth. The connection to outer space. The discovery of underground ecosystems on Earth has changed how scientists approach the search for extraterrestrial life. Planets and moons that were once considered uninhabitable are now being reconsidered. Some celestial bodies, such as icy moons with subsurface oceans, share similarities with Earth's underground environments. These environments may have liquid water beneath frozen surfaces. They may have chemical energy sources, and they may be isolated from external conditions. This creates the possibility that life could exist there. Not complex life, but microbial life, similar to what exists beneath Earth's surface. This is not speculation without basis. It is a scientific hypothesis supported by observable evidence. Earth provides the model. Other worlds may follow similar patterns. Hidden ecosystems in plain sight. Underground ecosystems are not limited to deep, inaccessible regions. Some exist in caves, aquifers, and soil layers relatively close to the surface. These environments may seem inactive, but they are not. They contain microbial communities that interact with minerals, water, and gases. They contribute to nutrient cycles. They influence groundwater composition. They play a role in larger ecological systems. Yet they are often overlooked because they are invisible. What cannot be seen is often underestimated. But in this case, invisibility does not equal insignificance. The challenge of exploration. Studying underground ecosystems is extremely difficult. Accessing deep environments requires drilling or excavation. These processes can disturb delicate systems. Maintaining uncontaminated samples is critical. Even small amounts of external material can alter the composition of the environment being studied. This makes research highly complex. Equipment must be carefully sterilized, procedures must be precise, and interpretation of data must account for potential contamination. Despite these challenges, discoveries continue. Each new sample provides insight into how life adapts to extreme conditions. Each new environment expands the scope of what is possible. Life that defies expectations. One of the most surprising aspects of underground life is its resilience. In environments with limited nutrients, organisms develop efficient metabolic processes. They use available resources with minimal waste. In some cases, they enter states of extremely low activity to conserve energy. This ability to persist under such conditions challenges conventional definitions of life. It suggests that life is not defined solely by activity or reproduction. It is defined by adaptability. And adaptability is far more widespread than previously assumed. The question of origins. The existence of life in extreme environments raises another question. How did it begin? One theory suggests that life may have originated in similar conditions. Deep beneath the surface, protected from external disturbances, sustained by chemical energy rather than sunlight. These environments would provide stability, conditions necessary for early life to form and evolve. If this is true, then underground ecosystems are not just examples of life in extreme conditions. They are potential windows into the origins of life itself. Misconceptions about hidden life. The idea of hidden ecosystems often leads to speculation. Some assume that such environments must contain unknown or advanced life forms beyond microbial organisms. However, scientific evidence does not support this. The organisms discovered so far are microscopic. They are simple in structure compared to complex life forms. But their simplicity does not diminish their importance. They provide insight into the limits of life, and they help define what is possible within known physical and chemical constraints. The focus is not on imagination. It is on evidence. The limits we have not reached. Despite decades of research, only a fraction of underground ecosystems have been studied. the vast majority remain unexplored. We do not know the full extent of these systems. We do not know how they interact with each other. And we do not know how many different types of organisms exist within them. This represents one of the largest frontiers in biological science. Not in distant space, but beneath our feet. Closing reflection. Life does not require the conditions we once thought were essential. It does not depend solely on sunlight, surface environments, or visible ecosystems. It exists in darkness. It adapts to extremes. It persists in places that challenge our understanding of biology. And it continues to be discovered in environments that were once thought to be empty. The deeper we look, the more we realize that life is not confined to the surface. It is embedded within the earth itself. And perhaps, if life can exist in such hidden places here, it may exist in hidden places elsewhere. Backhand index pointing right next step. Type Episode 6. Main Agla Episode Geological Forces We Can't Control Issy Cinematic. High Retention Documentary Style Main Likdunga. Episode 6. Clapperboard Episode 6. Geological Forces We Can't Control. The Earth is not still. From a human perspective, the ground beneath us appears stable. Buildings stand upright, roads remain fixed, cities are built on foundations we assume will hold for generations. But beneath that stability lies constant motion. The Earth is not static. It is dynamic, active, and constantly shifting, driven by forces so powerful that human structures are insignificant in comparison. These forces operate on scales that are difficult to observe directly. They build mountains, open oceans, trigger earthquakes, and reshape entire continents over time. And yet, despite their importance, we cannot control them. We can only observe, predict, and attempt to prepare, but never stop them. The engine beneath the surface. At the core of Earth's geological activity is internal heat. This heat originates from two primary sources: the residual heat from Earth's formation and the decay of radioactive elements within the planet. This energy drives movement within the mantle, a layer of semi-solid rock located beneath the crust. Although solid in structure, the mantle behaves like a slow-moving fluid over long timescales. Heat causes portions of the mantle to rise. As they rise, they cool. As they cool, they sink. This continuous cycle creates convection currents, massive, slow-moving flows that transfer energy throughout the planet. These currents are responsible for moving tectonic plates, the large sections of Earth's crust. And this movement is the foundation of nearly all major geological phenomena. The movement of continents. Continents are not fixed. They move, very slowly but constantly. Over millions of years, continents shift positions across the surface of the Earth. This movement is driven by the motion of tectonic plates beneath them. Where plates interact, different outcomes occur. When two plates collide, one may be forced beneath the other, a process known as subduction. This can lead to the formation of mountain ranges or volcanic activity. When plates move apart, new crust is formed as magma rises to fill the gap. When plates slide past one another, stress builds along fault lines, sometimes releasing energy in the form of earthquakes. These processes are not random. They follow physical laws. But the timing and intensity of their outcomes are not easily predicted. Earthquakes, sudden releases of energy. Earthquakes occur when stress accumulated along a fault is suddenly released. This release generates seismic waves, vibrations that travel through the earth and cause the ground to shake. The magnitude of an earthquake depends on the amount of energy released. Small earthquakes may go unnoticed. Large ones can cause widespread destruction. Structures collapse, ground shift, infrastructure fails. In extreme cases, entire regions can be permanently altered. The challenge lies in prediction. While scientists can identify fault lines and monitor seismic activity, accurately predicting the exact timing of an earthquake remains beyond current capabilities. Stress builds over time, but the exact moment of release is uncertain. This uncertainty makes earthquakes one of the most unpredictable natural hazards. Volcanoes, pressure from within. Volcanoes are another manifestation of internal geological forces. They form where magma, molten rock beneath the Earth's surface, reaches the surface through openings in the crust. This process can occur at tectonic boundaries or over hotspots within the mantle. When pressure builds beneath the surface, magma can rise, eventually erupting as lava, ash, and gases. Volcanic eruptions vary in intensity. Some are slow and relatively contained. Others are explosive, releasing massive amounts of material into the atmosphere. These events can affect local environments and, in some cases, global climate. Volcanic ash can block sunlight, leading to temporary cooling of the planet. This demonstrates how internal geological processes can influence surface conditions on a global scale. Plate boundaries, points of instability. Most geological activity occurs along plate boundaries, regions where tectonic plates interact. These boundaries are not stable. They are zones of constant motion and stress. There are three primary types of boundaries. Convergent boundaries, where plates collide. Divergent boundaries, where plates separate. Transform boundaries, where plates slide past each other. Each type produces different geological outcomes. Mountains form, ocean floors spread, faults develop. But these processes are not uniform. They vary depending on the composition of the crust, the angle of interaction, and the amount of force involved. This variability makes prediction difficult, and it ensures that geological activity remains complex and, in many cases, unpredictable. The scale of geological time. Geological processes operate on timescales that are far beyond human experience. What appears stable over decades or centuries may be changing slowly over millions of years. Mountains rise gradually. Erosion wears them down. Continents drift apart. Oceans open and close. These changes are continuous, but they are not visible in real time. This creates a disconnect between perception and reality. Humans experience Earth as stable, but in geological terms, it is constantly evolving. Human impact versus geological forces. Human activity has a measurable impact on the Earth. Construction alters landscapes, mining extracts resources, urbanization changes surface conditions. However, these changes are relatively small compared to natural geological forces. Earthquakes can shift land in seconds. Volcanoes can reshape entire regions in hours. Tectonic movement over millions of years can alter the positions of continents. Human influence operates on a different scale. It affects the surface. Geological forces shape the structure. This distinction is important. It highlights the limits of human control over natural systems. Monitoring the uncontrollable. Although we cannot control geological forces, we can monitor them. Seismographs detect ground movement. Satellites track changes in land elevation. Sensors measure volcanic activity. These tools provide valuable data. They help scientists identify patterns, assess risks, and develop early warning systems. But they do not provide complete certainty. Prediction remains an approximation. This limitation is not due to a lack of effort. It is due to the complexity of the systems involved. The hidden influence of the deep Earth. Beneath the crust lies a system that influences everything above it. Mantle convection drives plate movement. Core dynamics generate Earth's magnetic field. Internal heat regulates surface processes over long periods. These systems are interconnected. Changes in one can affect others. But because they operate deep within the Earth, they are difficult to study directly. Much of what we know is based on indirect observation. This introduces uncertainty. And uncertainty is a defining characteristic of geological science. Natural events beyond prediction. Some geological events occur with little to no warning. Sudden earthquakes, unexpected volcanic eruptions, rapid land shifts. These events highlight the limitations of current predictive models. While patterns can be identified, exact timing often cannot. This makes preparedness essential. Understanding risk does not eliminate it, but it allows for better response. The balance of forces. Earth's geological systems are in constant balance. Energy is released and absorbed. Pressure builds and is relieved. Material is created and destroyed. This balance maintains the structure of the planet over long periods. But it is not perfectly stable. It fluctuates, and those fluctuations can lead to significant events. Understanding this balance is key to understanding Earth as a system. Closing reflection. The forces that shape the Earth are powerful, persistent, and largely beyond human control. They operate beneath our awareness, influencing the world in ways that are often invisible until the effects are felt. We build our lives on a surface that is constantly in motion, and yet we treat it as if it is permanent. The reality is more complex. The ground beneath us is not fixed. It is part of a system that is still evolving, still shifting, still active, and still beyond our full control. Backhand index pointing right next step. Type Episode 7. Main Agla Episode Climate Systems. We do fully understand ISI, same cinematic documentary level Parlik Dunga. Episode 7. Clapper Board Episode 7. Climate systems we do fully understand. A system in constant motion. The climate is often described as the average of weather over time. But in reality, it is far more complex. Earth's climate is not a single system. It is a network of interconnected systems, oceans, atmosphere, ice sheets, land surfaces, and living organisms, all interacting with each other. These interactions occur continuously. Energy flows from the sun into the Earth's atmosphere. Heat is redistributed across the planet through winds and ocean currents. Moisture cycles through evaporation, condensation, and precipitation. Carbon moves between the atmosphere, oceans, and biosphere. Each of these processes influences the others, and together they form the climate system, a system that is still not fully understood. The role of the sun. The sun is the primary source of energy for Earth's climate. Its radiation drives weather patterns, ocean currents, and seasonal changes. But the sun's influence is not constant. It varies over time. Solar activity fluctuates in cycles, affecting the amount of energy reaching Earth. These variations can influence climate patterns. However, they do not fully explain the changes we observe today. Other factors are involved, and many of them are interconnected in ways that are still being studied. The atmosphere, a delicate layer. Earth's atmosphere is a thin layer of gases surrounding the planet. It plays a critical role in regulating temperature and supporting life. Greenhouse gases, such as carbon dioxide and methane, trap heat within the atmosphere. This process is essential. Without it, Earth would be too cold to support most forms of life. However, changes in the concentration of these gases can alter the balance. Increased greenhouse gas levels can lead to warming. This warming can affect weather patterns, sea levels, and ecosystems. But the exact relationship between emissions and climate response is not always linear. There are feedback mechanisms that can amplify or reduce the effects. Understanding these feedback loops is one of the greatest challenges in climate science. The ocean, Earth's heat reservoir. The oceans cover more than 70% of Earth's surface. They store vast amounts of heat and play a major role in regulating the climate. Ocean currents transport heat from the equator toward the poles. This movement influences temperature, weather patterns, and precipitation. But the ocean is not passive. It interacts dynamically with the atmosphere. Changes in ocean temperature can influence atmospheric conditions, and changes in the atmosphere can affect ocean behavior. This two-way interaction creates complex feedback systems, some of which are still not fully understood. El Niño and La Niña. One of the most well-known ocean-atmosphere interactions is the El Niño, Southern Oscillation. During an El Niño event, sea surface temperatures in the Pacific Ocean rise. This affects global weather patterns. Some regions experience increased rainfall. Others face droughts. La Niña represents the opposite phase. Cooler ocean temperatures lead to different climate impacts. These events occur irregularly. Their intensity and duration vary. And while scientists can identify their formation, predicting their exact behavior remains challenging. This highlights the complexity of climate interactions. Ice and feedback loops. Ice plays a crucial role in Earth's climate system. Polar ice sheets and glaciers reflect sunlight back into space. This helps regulate global temperatures. However, when ice melts, less sunlight is reflected. More heat is absorbed by the Earth's surface. This leads to further warming. This is known as a feedback loop. It is one example of how small changes can lead to larger effects. Other feedback loops exist within the climate system. Some amplify changes. Others help stabilize them. But many are not fully understood. Clouds, the uncertain variable. Clouds are one of the most complex elements of the climate system. They can both cool and warm the Earth. By reflecting sunlight, they reduce the amount of heat absorbed. By trapping heat, they can also increase warming. The net effect depends on the type, altitude, and composition of the clouds. This makes them difficult to model accurately. Cloud behavior remains one of the largest uncertainties in climate prediction. Even small changes in cloud formation can have significant impacts on global temperatures. Climate models, tools not certainties. Scientists use climate models to simulate Earth's climate. These models incorporate data from the atmosphere, oceans, land, and ice. They use mathematical equations to represent physical processes. Climate models are powerful tools. They help researchers understand trends and make projections. But they are not perfect. They rely on assumptions and approximations. And they cannot capture every detail of the real world. This introduces uncertainty into predictions. Despite this, climate models are essential for studying future scenarios. Abrupt climate change. Climate change is often viewed as a gradual process. But Earth's history shows that climate can change abruptly. Sudden shifts in temperature have occurred in the past. These events can happen when tipping points are reached. A tipping point is a threshold beyond which a system changes rapidly. Once crossed, the system may not return to its previous state. Examples include the collapse of ice sheets or changes in ocean circulation. These events are difficult to predict, and their consequences can be significant. The ocean conveyor belt. One of the most important systems in climate regulation is the global ocean circulation system. Often referred to as the conveyor belt, it moves warm and cold water around the planet. This circulation helps regulate climate by distributing heat. However, changes in temperature and salinity can disrupt this system. If altered, it could lead to significant climate shifts. Some studies suggest that parts of this system may already be changing, but the full implications are not yet clear. The carbon cycle. Carbon moves through the Earth in a continuous cycle. It is stored in the atmosphere, oceans, soil, and living organisms. Plants absorb carbon dioxide during photosynthesis. Oceans absorb and release carbon. Animals and humans contribute to the cycle through respiration and activity. This cycle helps regulate atmospheric carbon levels. However, human activities have increased the amount of carbon in the atmosphere. This has altered the natural balance, and the long-term effects of this change are still being studied. The limits of prediction. Despite advances in technology and science, predicting climate remains a challenge. The system is too complex, too interconnected, too sensitive to small changes. Even minor variations in initial conditions can lead to significantly different outcomes. This is known as sensitivity to initial conditions. It is one of the reasons why long-term climate prediction is difficult. Scientists continue to improve models and gather data, but uncertainty remains an inherent part of the system, a system we depend on. The climate system supports life on Earth. It regulates temperature, water availability, and ecological balance. Every living organism depends on it, from the smallest microbe to the largest ecosystem. Yet it is a system we do not fully understand. This does not mean we are powerless, but it does mean we must approach it with caution and with respect. Closing reflection. The climate is not just a backdrop to life. It is an active, dynamic system, one that responds to both natural and human influences. It evolves, it adapts, and it changes in ways that are not always predictable. Our understanding of this system is still incomplete, but it is growing. With each discovery, we come closer to understanding the forces that shape our world. But some aspects remain uncertain, and perhaps they always will. Backhand index pointing right next step. Type Episode 8. Main Agla Episode Unknown Energy and Natural Phenomena Likhunga, or Fur Opka Complete Documentary Series, or by Powerful Hoda Jayega. Episode 8. Clapperboard Episode 8. Unknown Energy and Natural Phenomena. Forces we cannot see. Throughout history, humans have attempted to explain the world using observation and logic. We have identified gravity, electricity, magnetism, and nuclear forces. These are the known forces that shape reality. But what if there are others? For centuries, unexplained phenomena have been reported, events that do not fit within established scientific frameworks. Mysterious lights in the sky, unusual energy fluctuations in remote locations, sudden environmental anomalies with no clear cause. These phenomena raise a fundamental question. Is everything already known? Or are there hidden forces still waiting to be discovered? Energy in the natural world. Energy exists in many forms. Kinetic energy, thermal energy, electromagnetic energy, chemical energy. These are well understood. But energy in nature does not always behave in predictable ways. In some environments, energy appears to concentrate in unusual patterns. In others, it dissipates in ways that are not fully explained. Scientists continue to study these behaviors. But not all energy interactions are fully mapped or understood. There may be processes occurring at micro or macro levels that remain hidden from current detection methods. Electromagnetic anomalies. Earth is surrounded by an electromagnetic field. This field protects the planet from solar radiation. It is generated by the movement of molten iron in Earth's outer core. However, this magnetic field is not uniform. In certain regions, anomalies have been detected, areas where the field behaves differently than expected. One well-known example is the South Atlantic region, where satellites experience increased radiation exposure. These anomalies are studied carefully, but their long-term behavior and implications are still being researched. They remind us that even fundamental forces like magnetism can have unpredictable variations. Natural radiation sources. Radiation is a natural part of Earth's environment. It comes from the sun, from cosmic sources, and from radioactive materials within the Earth. Most radiation is harmless at normal levels. But in certain locations, radiation levels can vary significantly. Geological formations can concentrate radioactive elements. This can create areas with elevated radiation. The reasons behind these concentrations are not always fully understood. They depend on complex geological processes that have occurred over millions of years. Mysterious atmospheric phenomena. The atmosphere is a dynamic system filled with energy. Weather events are well studied, but some atmospheric phenomena remain difficult to explain. Transient luminous events, such as sprites and blue jets, occur above thunderstorms. These events involve bursts of light high in the atmosphere. They were only recently discovered and are still being studied. Other phenomena include unexplained atmospheric lights and rare optical effects. While some are now understood, others remain under investigation. These events suggest that the atmosphere may still hold undiscovered behaviors. Earth's electrical activity. Lightning is one of the most visible forms of electrical energy in nature. It is powerful and unpredictable. Lightning strikes can transfer enormous amounts of energy in a fraction of a second. But not all electrical activity behaves the same way. In some cases, electrical discharges occur without clear causes. Unusual patterns of lightning have been observed in certain regions. These include events that defy typical storm behavior. Scientists study these occurrences to better understand atmospheric electricity. But the complexity of the system leaves many questions unanswered. Geological energy release. Energy is not only present in the atmosphere. It is also stored beneath the Earth's surface. Earthquakes and volcanic eruptions release this stored energy. But there are also smaller, less understood releases of energy. In some locations, unexplained vibrations or heat emissions have been recorded. These may be linked to geological processes not yet fully understood, or they may be part of known processes that behave differently under specific conditions. Either way, they challenge our current understanding of Earth's internal energy systems. Plasma and high-energy states. Plasma is often referred to as the fourth state of matter. It consists of ionized gas with free-moving charged particles. Plasma is found in stars, lightning, and certain laboratory conditions. It behaves differently from solids, liquids, and gases. In space and in Earth's upper atmosphere, plasma plays a significant role. But its behavior can be highly complex. Interactions between plasma and magnetic fields can create unusual effects. Some of these effects are still being studied. They may help explain certain natural phenomena that appear unusual or unexplained. The boundary between known and unknown. Science has made incredible progress in understanding energy. But the boundary between known and unknown still exists. As measurement tools improve, previously unknown phenomena become observable. This has happened repeatedly throughout history. What was once unexplained is now understood. But each discovery often leads to new questions. This cycle of discovery continues, expanding our knowledge while revealing the limits of what we currently know. Unexplained observations. There are recorded instances of natural events that do not fit easily into known scientific categories. Reports of unusual energy emissions, unidentified atmospheric disturbances, environmental anomalies without clear explanations. These observations are often difficult to verify or reproduce, but they continue to appear in different contexts. Scientists approach such reports with caution, seeking evidence, patterns, and reproducibility before drawing conclusions. This ensures that science remains grounded in verification. But it also means that some phenomena remain unexplained for longer periods. Technology and detection limits. Our ability to detect and measure energy depends on technology. As technology improves, our understanding expands. But all instruments have limits. They can only measure certain ranges of energy. They can only detect certain types of signals. This means that some forms of energy or phenomena may exist outside our current detection capabilities. This limitation does not imply that these phenomena are beyond science. It simply means they have not yet been measured or observed in a controlled way. The role of interdisciplinary science. Understanding unknown energy and natural phenomena requires multiple fields of study. Physics, geology, atmospheric science, astronomy, and chemistry all contribute. Each field provides a piece of the puzzle. By combining these perspectives, scientists can build a more complete picture. This interdisciplinary approach is essential for studying complex systems, because no single field can explain everything on its own. A universe of possibilities. The Earth is part of a much larger system, the universe. And the universe itself contains countless forms of energy and matter. Dark matter and dark energy are examples of components that are not fully understood. They make up a large portion of the universe, but their exact nature remains unknown. This suggests that there may be fundamental aspects of reality that are still beyond our comprehension. And these unknowns may influence natural phenomena in ways we have not yet identified. Closing reflection. Nature is full of energy. Some of it we understand. Some of it we observe but cannot fully explain. And some of it may still be undiscovered. The more we learn, the more complex the picture becomes. Unknown energy and natural phenomena remind us of the limits of our current knowledge. But they also represent opportunity. The opportunity to discover, to understand, and to expand the boundaries of science. Backhand index pointing right next step. Type Episode 9. Fur main op key li scientific discoveries that changed everything cinematic documentary style main lik dunga. Episode 9. Clapperboard Episode 9. Scientific discoveries that changed everything. Moments that redefined reality. History is filled with moments that fundamentally changed how humans understand the world. Discoveries that did not just add knowledge, but transformed it. These breakthroughs reshaped science, altered beliefs, and expanded the limits of what was thought possible. Each discovery began with a question, and each answer opened the door to an entirely new understanding. But these moments were not always immediate. Many were met with resistance. Some were misunderstood. Others were ignored. Yet over time, they proved to be some of the most important advances in human history. The law of gravity. One of the most influential discoveries in science is the understanding of gravity. Before this, motion and falling objects were not fully explained. Then came a unified explanation for why objects fall and how planets move. This discovery connected the motion of objects on Earth with the motion of celestial bodies. It revealed that the same force governs both. Gravity became a foundational principle in physics. It allowed scientists to predict planetary motion. It explained tides, orbits, and the structure of the solar system. And it remains one of the most important forces in understanding the universe. The nature of light. Light has fascinated humans for centuries. Is it a wave? Is it a particle? Or something else entirely? The study of light led to groundbreaking discoveries in physics. It revealed that light behaves in both wave-like and particle-like ways. This dual nature challenged classical physics, and it introduced new concepts that helped shape modern science. Understanding light also led to the development of technologies such as microscopes, telescopes, and lasers. Each advancement expanded our ability to observe and analyze the world. The structure of the atom. For much of history, atoms were considered the smallest units of matter. But further investigation revealed that atoms themselves are made of smaller particles: protons, neutrons, and electrons. This discovery opened the field of atomic physics. It led to an entirely new understanding of matter and energy. And it paved the way for technologies such as nuclear energy and medical imaging. The atom is now known to be a complex system, one that contains immense energy and potential. The theory of evolution. Life on Earth is diverse and constantly changing. The theory of evolution provided a framework for understanding how species develop over time. It explained how organisms adapt to their environments, and how new species emerge through gradual changes. This theory reshaped biology. It connected all life through common ancestry, and it provided a scientific explanation for biodiversity. While widely accepted today, it was once highly controversial. But evidence from fossils, genetics, and observations continues to support it. The discovery of DNA. DNA is the molecule that carries genetic information. Its discovery revealed how traits are passed from one generation to the next. This breakthrough transformed biology and medicine. It allowed scientists to understand heredity at a molecular level. And it opened the door to genetic research, including gene editing and biotechnology. DNA is now central to fields such as forensic science, medicine, and evolutionary biology. It provides a blueprint for life itself. The expansion of the universe. For a long time, the universe was thought to be static. But observations revealed something unexpected. The universe is expanding. Galaxies are moving away from each other. This discovery changed our understanding of the cosmos. It suggested that the universe had a beginning, and that it continues to evolve over time. This led to new theories about the origin and future of the universe, and it remains one of the most important discoveries in cosmology. The power of electromagnetism. Electricity and magnetism were once studied separately, but they were later unified into a single theory. Electromagnetism explains how electric currents and magnetic fields interact. This discovery revolutionized technology. It led to the development of electric power, communication systems, and modern electronics. Without this understanding, many aspects of modern life would not exist. Electromagnetism is one of the fundamental forces that shape the physical world. The discovery of radioactivity. Radioactivity revealed that atoms are not always stable. Some elements emit energy in the form of radiation. This discovery opened new fields in science and medicine. It also led to the development of nuclear energy. Radioactivity has both beneficial and harmful applications. It is used in cancer treatment and medical imaging, but it also requires careful handling due to its potential risks. This discovery changed how scientists view the structure of matter. Quantum mechanics, a new reality. At very small scales, the laws of physics behave differently. Quantum mechanics describes the behavior of particles at atomic and subatomic levels. It introduced concepts that challenged classical understanding. Particles can exist in multiple states. Their behavior can be probabilistic rather than deterministic. This field has led to major technological advancements, including semiconductors, lasers, and quantum computing. But it also raises deep philosophical questions about the nature of reality. The speed of light. The speed of light is one of the fundamental constants of the universe. It defines the maximum speed at which information can travel. This discovery reshaped physics and cosmology. It led to the development of relativity theory, which explains how space and time are interconnected. This understanding has practical applications in technologies such as GPS systems, and it remains a key concept in modern physics. The role of scientific discovery. Scientific discoveries do more than explain the world. They change how humans think. They shift perspectives. They challenge assumptions. And they open new possibilities. Each discovery builds upon previous knowledge, creating a chain of understanding that continues to evolve. Science is not static. It is a continuous process of questioning and discovery. Unanswered questions remain. Despite these advancements, many questions remain unanswered. Dark matter, dark energy, the origin of life, the nature of consciousness. These are areas where science continues to explore. They represent the frontiers of knowledge, and they remind us that there is still much to learn. Closing reflection. Scientific discoveries have transformed humanity. They have expanded our understanding of the universe, and they have changed the way we live. But they have also revealed how much we still do not know. Each answer leads to new questions. Each discovery opens new doors. And the journey of understanding continues. Backhand index pointing right next step. Type episode 10. Final episode main the future of exploration and final truth co-cinematic or powerful ending key Sath complete Karunga Jo Opk series co-viral level P Laya Sakta High. Episode 10. Clapperboard Episode 10. The future of exploration and final truth. The endless drive to explore. From the earliest moments of human history, exploration has been a defining trait. We crossed oceans. We climbed mountains. We mapped the unknown. Each generation pushed further than the one before it, driven by curiosity, by necessity, and by the desire to understand what lies beyond the horizon. But exploration has not stopped. It has evolved. Today, the frontiers are no longer just physical. They are scientific, technological, and even cosmic. And the next phase of exploration may redefine what it means to be human. The last unexplored frontiers on Earth. Despite centuries of exploration, parts of Earth remain unexplored. Deep ocean trenches still conceal mysteries. Remote regions of Antarctica hold secrets beneath miles of ice. Dense forests and underground systems continue to hide unknown ecosystems. These environments are difficult to access, and even more difficult to study. But they are not empty. They are part of Earth's living system. and they may contain answers to questions we have not yet asked. The deep ocean, a hidden world. The ocean remains one of the least explored regions on Earth. Its depths are extreme, its pressure is immense, and its environment is largely inaccessible. Yet life exists there, adapted to darkness, adapted to pressure, adapted to conditions that would be hostile elsewhere. Scientists continue to discover new species in these depths. Each discovery expands our understanding of life and suggests that there is still much we do not know about our own planet. Space, the ultimate frontier. Beyond Earth lies space, a vast, seemingly endless expanse filled with stars, planets, and galaxies. Humanity has already taken steps into this frontier. But compared to the scale of the universe, our presence is minimal. There is still much to explore. New worlds, new systems, and possibly new forms of life. Space exploration is not just about discovery. It is about understanding our place in the universe and the conditions that allow life to exist. The search for extraterrestrial life. One of the most profound questions in science is whether life exists beyond Earth. Astronomers search for planets within habitable zones. Scientists analyze atmospheric composition for signs of life. And missions are sent to explore moons and planets that may harbor the right conditions. So far, no definitive evidence of extraterrestrial life has been found. But the search continues, and each discovery brings us closer to answering one of humanity's greatest questions. Advanced technology and exploration. Technology is rapidly advancing. Artificial intelligence, robotics, quantum computing. These tools are transforming how we explore and understand the world. Robots can reach places humans cannot. AI can analyze massive datasets in seconds. Sensors can detect signal previously beyond our capabilities. These advancements are accelerating discovery and expanding the boundaries of what is possible. The role of artificial intelligence. Artificial intelligence is becoming an essential tool in exploration. It can identify patterns, predict outcomes, and assist in analyzing complex systems. In fields like astronomy, climate science, and geology, AI is already making significant contributions. It helps process data from distant galaxies. It models climate systems, and it assists in identifying geological risks. But AI is not just a tool. It is a new way of interacting with information, and it may play a central role in future discoveries. Human limits and machine expansion. Humans have physical and cognitive limits. We cannot travel indefinitely. We cannot process infinite data. But machines can extend these limits. They can operate in extreme environments. They can process vast amounts of information. And they can function continuously without fatigue. This partnership between humans and machines is reshaping exploration. It allows us to go further and understand more than ever before. The unknown future. The future of exploration is uncertain. New discoveries will be made. New technologies will emerge. And new questions will arise. Some of these questions may challenge existing knowledge. Others may redefine it entirely. But one thing is certain. The unknown will always exist. Because as long as we learn, there will always be more to discover. The final truth. If there is one truth that defines exploration, it is this. We are always at the beginning of understanding. No matter how much we learn, no matter how far we go, there will always be more. More to see, more to study, more to question. The Earth is vast. The universe is even larger. and knowledge is constantly expanding. The final truth is not an answer. It is a realization. That discovery is endless. Closing reflection. This journey has taken us through hidden worlds, through forces we cannot control, through systems we do not fully understand, and through discoveries that changed everything. But the story does not end here. It continues. With every question asked, with every experiment conducted, with every mystery explored, the future belongs to those who seek answers. And the search is far from over.